I want to take a quick look at the bell-shaped distribution, also known as the normal distribution. So the right-hand side and the left-hand side, they have about the same amount of data. It's not skewed, there's no outliers, and when you're dealing with a large amount of data, real-world data, you'll find that it tends to fall into this category. So let's take a look at a couple of examples. The first one is birth weight. This is an excellent example of where normal distribution is seen throughout the world. Also, female shoe sales. You're not going to sell very many size 14s or size 4. You're going to sell right in the middle, right at where my shoe size is at 8. Also, here's IQ graph. Here's a graph where you take two dice and you sum them together. So if you're ever going to bet on the sum of two dice, you better bet on 7. The height around the world is also normally distributed. And this was an example we looked at just the other day. Hollywood movies and the audience score. It's not quite normally distributed, but if we continued collecting data for this, you would see that it would really start looking more in that normal pattern. One descriptive statistic that we use a lot is called the mean. The sample mean is represented by x bar, while the population mean is represented by mu, or like a squiggly m. So the mean is the sum of all the data values divided by the number of data values that you have. And if you notice, there's like an E there, and that is a symbol for sum. Another statistic that we use a lot is called the standard deviation. And the standard deviation gives a rough estimate of the typical distance the data values are from the mean. The larger the standard deviation, the more variability you're going to have with your data and the more spread out your data is going to be. So this calculation right here, what that means is we take the distance each data value is from the mean, square those, add them all together, and then divide by 1 less than the number of entries that you have. Once you have that number, then you square root it, and that gives you the standard deviation. The sample standard deviation is S, while the population standard deviation is sigma. And we're actually going to be letting our calculator take the lead on this one. So here's a histogram with a standard deviation of 1 compared to a histogram with a standard deviation of 4. The 4 looks very spread out, while a standard deviation of 1 seems like it's really clumped together. But if I take these two charts and I change the x values, what we're going to find is that I can make them look almost identical just by changing the domains. One generic rule to keep in mind is the 95% rule. What this means is that 95% of your data should fall between two standard deviations of the mean if it's a normal distribution. A more precise rule is the empirical rule, which states that within one standard deviation of the mean, you should find 68% of your data. Within 2 standard deviations, we've got 95%, and within 3 standard deviations, we should have almost all of our data, or 99.7% of the data, within 3 standard deviations of the mean. The z-score is an important number because it tells us where our data value is in the distribution. If it is really close to the mean, it'll be close to 0. If it's above the mean, it'll be a positive number, and if it's below the mean, it'll be a negative number. In a normal distribution, where 95% of your data is between 2 standard deviations, your z-scores will generally fall between -2 and 2. So here's how you calculate the z-score. First, you take your score and you subtract it from the mean, or mu. Then you're going to divide by the standard deviation, or sigma, and that's going to tell us how many standard deviations our score is from the mean. So let's take a look at an example. So which is better, an ACT score of 28 or an SAT score of 2100? The ACT, the mean is 21 with a standard deviation of 5, and the SAT, the mean is 1500 with a standard deviation of 325. So assuming that both of these are normally distributed or bell-shaped, we're going to need to use z-scores to actually find out how far they are from the mean, and we're going to choose which one's larger. So the first thing I'm going to do is I'm going to take my score of 28 and I'm going to subtract my mean from it, then I divide by 5, and so I get a z-score of 1.4. Then I'm going to take my 2100 and subtract my mean from it of 1500, divide by 325, and I get a value of 1.85. So once we've done our calculations, we can think about, is a score of 1.4 or 1.85 actually better? So let's take a look at our normal distribution here. 1.4 is about here, while 1.85 is here. And so we can see that 1.85 standard deviations above the mean is a better score than just 1.4.